There it goes. Okay, I think the live stream has started. Let me get me up there. So, our goal today is to continue talking about forces. And one of the things you're going to find out today is geometry and coordinate systems we have to deal with all the time. And sometimes coordinate systems get tricky. Sometimes plus minus signs get tricky. And sometimes problems have more than one angle. And so rather than beat around the bush, let's start doing problems and see what are some of the issues that come up. Now, I'm going to do a screen share. Give me a sec. You don't need to see my email. Let's go to this one instead. All right. So in this case, I'm looking at questions 5.9 and 5.10. I'm going to do exactly the same questions that I did in the earlier session. So if you already watched that live stream, you could probably just take off. That said, there are some tricks in here, and so I think it's worth doing them again. I do want to point out that I didn't do question 5.8, so you'd better do that one on your own later. And but let's practice these ones. These ones are probably a little trickier. So without further ado, let's look at question 5.9. You got a zombie. A lot of these problems I'm going to put zombies in. I was on a zombie kick when I was writing the book. So there's a lot of zombie questions. Zombie pulls a suitcase up a ramp. There's an unknown tension at some angle phi. Okay, friction is negligible. That's what I was looking for. Okay, so there's no friction in this case. All right, and then we've got a mass, and we're told some angles. Okay, got it. So I'm going to get started drawing this up on my page. I'll let you kind of read this. If you want to, this is what you could try to do. Try to draw the FBD and the force equations without looking at the solutions. I'm not going to draw it all. I'm just going to get the picture, and I'm going to go through it with you. But if you want to do something while you wait for me, try to think to yourself what the FBD would look like. All right. And then we're going to do it all together. Okay, I didn't use any color. Good. All right. And so you've had a chance to look at it. And if anything, hopefully what that was supposed to do is make you at least realize, wait a minute, I have to think a little bit now. This isn't just something easy. With the elevator problem, it was really easy to kind of see things and you could write it down quickly. When we start getting angles involved, it slows the process down tremendously. So I'm going to try and draw this on there. There is a force. The magnitude is t. The direction is this way. Together, these are the force vector. And those are the components. That angle is phi. That looks pretty sloppy. There we go. That's a little better. Notice you're going to hear me hammer on this. Theta and phi are different angles. Make sure when you're writing them differently. Okay, phi's got that nearly vertical line. Just a lot of problems in the real life have more than one angle, so you got to know how to write a couple of different symbols. All right, that force I know is there. Somebody go ahead and hit unmute and tell me another force. Anything.
Gravity.
Gravity. Which direction does gravitational force act on this thing?
Down.
Or... Yeah, exactly. Straight down. So let me ask, is it like A or is it like B? Is it like A or is it like B?
More like B.
Exactly, straight down. Now my picture might be crappy because I'm drawn from the side, but nice job. Now, a lot of times, I don't know if you notice this, but when I'm writing out problems and I don't know which way things are going to split up into components, a lot of times I write the force magnitude near the arrowhead. That way I have space to move it around. Sometimes I'll literally write it over here, just way out of the way. But yeah, in this particular problem, I think I want to label it on this side. So I'm going to label it right there. You can always erase your label and move it, right? There we go. Okay, so there's mg. What's another force acting on this thing?
Normal force.
Normal. Which way does that point?
Up, I believe.
Like this?
Yes.
And that's not right. And that's what I was looking. This is a trick one. Remember what normal means in mathematics. Normal means perpendicular. So if you're sitting on a flat surface like this one up here, you're right. This one, the normal force is straight up. But if you're on an angle, the normal force gets angled as well,
I
right?
see.
So then it's actually more like that. Does that make sense? Slightly
Yes.
angled. Nice job. Okay. So that's why I like to call it normal, because then eventually you start to remember, oh yeah, normal means perpendicular in math. All right. So now you could choose lots of different coordinate systems. Like one that you might choose is maybe the normal XY, where it's like this and like that. That one gets kind of tricky. I know from experience this problem is best solved by rotating the coordinate system. Because I could see that some of these arrows start to line up on this thing. Do you see that? Whoa, this is kind of sloppy, isn't it? Hopefully that looks a little better. It's not perfect. Sorry about that. I'm going to make this MG a little bit longer just so I can have more room. Okay, sorry about that. Okay. In this case, notice we have to figure out some angles in here. So I want to point something out. This is a trick I use all the time. I call it the skinny triangle trick. Look at this angle down here, theta. I deliberately drew it very skinny as a small angle. And by that, I mean something that's much smaller than 45 degrees. Okay. I deliberately chose an angle significantly smaller than 45 degrees. It makes it easier for me to check my work. And I'll explain. We're going to use this particular figure so many times that I want to go through it slowly. What does this angle right here look like that I'm pointing at with the marker?
It's 90.
90. So what is this angle up here that has a black dot in it? What's that angle going to be?
90 minus theta.
Exactly. So just in case you don't see that, the total number of degrees in a triangle is 180. Well, I've got 90 degrees from this right angle plus theta plus that black dot angle. And so in this case, if I subtract this over, I get 90 minus theta equals the black dot. So far, so good? If you need me to do that again, we could do it again later. So there's that. So I just wanted to point out another way you think about it is the right angle takes 90 degrees. There's 90 degrees left for the other two in a right triangle. So that's 90 minus theta. what's left for this angle right here? I'll put 2 black dots in there. What's that double dot angle? I'll give you a hint. What's this? How about I draw 3 lines over here? What's the triple dot look like?
It looks like a 90.
It is, right? Because remember, the normal force is perpendicular, so shouldn't this line that runs through it be perpendicular? You bet. So that's a right angle. So what's left for the double dot?
I think it's theta.
It's theta. Now you see the advantage of the skinny triangle trick. Doesn't it just look like theta? It does. So that's a way I check my work. It looks like that. If you draw all your angles at 45, you can't use that. But look at this. The sum of all of these angles is 180 degrees. That should equal 90 minus theta plus double dot plus 90 degrees, right? And when you work all that out, you get theta equals double dot, right? So this angle in here is also theta. Or think about it like this. If this is a right angle, this whole thing right here is a right angle, right? If that's a right angle, these two have to add up to 90. Well, theta plus 90 minus theta is 90. Okay, so notice that geometry is a huge portion of your physics abilities here. All right, next. Okay, so before we go on, if I want to use this as my coordinate system, I'm going to draw it over here. I'm trying to use this as X and this as Y. What's the acceleration in this particular problem? Do you know? Does it say it or not? Excuse me.
Well, so the zombie's pulling at constant speed, so I guess there's 0.
Nice. Does that make sense? Now, we should be careful. It is possible to have constant speed and acceleration if you're moving in a circle, because then your velocity, which includes the direction, but that's physics 161. For this class, constant speed, constant direction, that means velocity is constant, not just speed. So this constant speed and direction means constant velocity. Constant velocity, not constant speed, is what really means acceleration equals 0. All right, that's cool. All right, so that's good. Now, we need to split up these forces according to this coordinate system. N doesn't need splitting up. T is kind of already split up. Look at this one down here. We've got to work on this mg. Now, in this case, I'm going to draw a couple of lines here, and I want you to choose. Look at question, okay. Whoops. It's kind of hard to fit these in. A, B, and C. Which of these lines, that's supposed to be a letter B, which of those lines best represents the correct way to split up mg? Is it line A, line B, or line C? What do you think?
Would it be A?
Exactly. How can you tell? What was your thought process?
Because it has to make a 90-degree angle.
Exactly. We need this to be a right angle, not that. Sorry. Yeah, we need this to be a right angle, not that, is what I meant to say. Another way I would say it is, notice this is the line that's parallel to the x-axis. The whole point in splitting up vectors is to split it up so that the vectors are parallel to the axis. So if I could, let me draw this now. So that needs to be the right angle. I like to think of this another way. This is the original vector. The components of the vector, you're splitting up the vector into components. The components must be smaller than the vector itself. If you had done this, notice this side is longer than that. That wouldn't have worked. So, right, that would indicate the components are longer than the vector itself, and that's incorrect. So watch out for that. Now, some of you I know probably had high school physics and probably do this. You just tilt this thing like this on your paper, right? And you draw it like that. I recommend not doing that. I recommend just drawing it as the forces appear in nature for a couple of reasons. I think number one, that more accurately reflects the actual situation. Number two, that will help you practice for circular motion problems where they get tricky no matter what you try to do. And number three, I have seen a lot of students accidentally put mg pointing the wrong way when they switch these things. So what I'm saying here is, if you learned this in high school, a lot of kids in high school would go like this. They would rotate it in their mind. And then what they'll do is they'll put mg like this. Whoops. And notice this is actually the wrong way. Sometimes, and I don't know why, it's because many problems have ramps this way and that way, I think. But if a problem has a ramp this way or that way, the angle at which you move mg changes depending on which way the ramp points. And students get in this habit of doing this, try to rotate it all in their head, and they screw it up. So I don't recommend doing that. That said, if it gets the right answer, more power to you. Okay. So I do think this is right for several reasons. And this is how I write my solutions. So if you want to understand my solutions, I recommend you learn this method. All right. Now, does that look like a pretty good free body diagram to you? Anything? Any thoughts about that? Any questions?
I mean, wouldn't you want to avoid having any surface there if you're
Exactly. You caught it. This is not a free body diagram. It's very close to one. The ramp is a second body. And it's actually adding a lot of confusion with a lot of extra lines. So check this out, people. I know you want to get done with your physics as quickly as possible, but sometimes, and this is one of them, it actually benefits us to draw some stuff on here to get a feeling for it, then immediately draw it again more neatly without the other body, without the ramp. Excellent, Jake, you caught it. So I'm going to redraw this, and you could redraw it as well. All right. Obviously, you have the live stream to go back. Whoops. All right, but so what I'm going to do is put a dot here. I know I had mg down, and now it's really easy to split this up. We already know that that's theta from our earlier drawing, and this is mg. We also had this was T, the zombie is pulling. This angle was phi. It was not necessarily the same angle. And then we had the normal force. That is now an FBD, right? That's supposed to be an X, by the way. Okay. So now, what do you do with this? Well, let's write down the sum of forces in the X direction. Remember, these come from the arrows. Oh, we'd better get our SOHCAHTOA crap figured out. Do you see that? What is this side right here? Is this going to be mg cosine or mg sine of theta? What do you think? What's this side?
mg sine of theta.
Sine, because opposite. What's this side then? Probably mg cosine. Adjacent. And then in this one, what's this component right here? Somebody else. Is it t cosine of phi or t cosine? Wait, did I say t cosine or t sine? What is this one?
T cosine.
I think so. Adjacent. So SOHCAHTOA. Ka uses adjacent. This is adjacent to phi. Looking good. So that means this must be t sine. All right. So now we're ready to do this. Now that I know what the arrowheads each represent, give me one arrowhead that's parallel to the x-axis and tell me what it is in plus or minus.
We have positive t cosine phi.
Correct. Somebody else. Is that it, or are we done, or is there any more?
Negative mg sine theta.
Okay. Negative. This arrowhead points opposite that. I agree. Negative. Good. Anything else, or are we done with the X? I think that's it in the X. Do you agree? I hope so.
Yeah.
Oh, good. Yeah. All right. So all this is equal to what in this case?
0, because no acceleration.
Nice. I'm going to take those dots out of there, just so I'm not messing up my pretty board. All right. So now let's do okay, I got to lower this just a little bit. So we're doing the Y direction now. Okay, give me one force in the Y, somebody.
We've got the positive normal force.
Positive normal force. N, yep. Somebody else. What's another one? Or are we all done?
T sine. I forgot the name for it.
Phi.
Phi. Yeah.
Yep, excellent.
T,
Is that going to be positive or negative according to this coordinate system?
positive.
Correct. Nice job. And is that it, or is there more? Somebody else. Excuse
What
me.
about mg cosine
I agree. Positive or negative?
negative?
Mm-hmm. Nice job. Theta or phi? Theta. Okay, got it. What's that all going to equal in this case? 0. What do you think? Just so you know, when these problems appear on your final exam, What we've just shown here is usually 2/3 of the points. So a lot of times I'll give 4 points for free body diagrams, 4 points for force equations, and then 3 points for an answer. It's like, this is the physics to me, because the rest is math. It's algebra. So if you look at the questions now, let's go back and look at them. The next part is determine T and determine N. So notice all the work is basically here. At this point, if I want to solve for T, which equation looks better, X or Y?
X.
X. We're told in the problem that the angles are known, M and G are known. We got it pretty quickly. And then if you want to get the normal force, just describe how you would get the normal force. We don't have to do it. How would you do it? Excuse me. What is the kind of like the procedure you would follow?
Can
Go
you
ahead.
solve for T and plug in?
Yep. Now, here's a subtle little thing. That's absolutely right. The only thing I would add to that is make sure you solve this one for N first and then plug in. Because think about it, T is going to be some big ugly mess. Well, it's not that bad, but it's just a little bit easier if you first solve for N, then plug in what T. So that was excellent. Nice job. Right on. Okay. Hopefully you're feeling better on this. A lot of students at this point are like, you know what? I kind of like this more than projectiles and kinematics. And I think what you'll find is by the end of the semester, when you go back to study for the final, you'll look at chapters 1 through 4 and be like, wait, it's not as bad now. Somehow, right about this time, students start to get it and they get used to the symbols, and it's just not as confusing after this chapter. I don't know why. I see this every year. Every year students say, oh, this is a lot better than the last stuff. Turns out you're just getting better. That's what it is. So hopefully you find that to be true about yourself right now. You're thinking, oh, I got this a little bit. I hope so. Let's go look and see if there's anything else in the solution that's worth noting. Oh, I will say one last thing while we're on this. Because you're going to do algebra with this afterwards, and because this is such a huge part of the points, typically you have to pick and choose your spots to check your work on your test because you don't have an infinite amount of time in the real world. This is one of those spots you should double check. Double check the arrowheads and stuff. Notice how slowly I was going through them, like checking and pointing at stuff on my paper, thinking like, okay, plus, 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 negative, negative. Okay, got it. And so double checking your signs, double checking whether you use the right angles, theta or phi, before you go on. It's pretty nice because once you start doing algebra, it's going to go really quickly and you're never going to spot your mistakes. So this is the time to check for mistakes before you go on. All right, let's get into here. See if there's anything else. Okay, so there it is. There's the result. And then notice what I did. I actually did this. I solved for N, and then I plugged in the crap. And notice I actually factored it out. This is nice because what's something you should do with every physics answer that's algebraic? Do you guys remember? Check the
Units?
units. Well, let's say, notice, even though it takes a little bit of algebra, this is actually easy. What are the units of this crap here in parentheses? That stuff right there. What are the units of that crap? These are
No
functions. Yeah, no units. They're all functions, so there's no units. Right? So what are the units of lowercase n? It's normal force. What are the units of a force?
Newtons?
Newtons, capital N. And then remember, I said the units of force are kilogram meter per second squared, which is a unit, right? So this has the right mg, I know is a force. So this is also a force, but it's kilogram times meter per second squared, which is the same thing as a Newton. Said another way, the units of mg equal the units of force. And you might be saying, well, why would I remember that? Most forces, we oftentimes will talk about an object, the forces on an object relative to its weight, right? So weight is one of the forces acting on an object. So it's easy. What we've done is we've clarified that the normal force is not necessarily equal to the weight. It's the weight times this screwball factor over here, this sine, cosine, tangent thing. All right, check the units. And then another thing you could do is sometimes you could check special things like what if the angles go to 0 and stuff like that. But definitely always check the units. Questions about that before we go to the next one?
So I guess all the physics makes sense, but like I took geometry back in high school, so I need to find like some sort of resource that kind of can remind me how to figure out all these like relative angles.
I'll
Do you
teach
know
you
anywhere?
in class.
Okay.
Because we're going to do practice. We're going to just keep practicing them. And then we could also talk at office hours if you want to remember. There's a few that we use all the time. And I happen to know the next problem that we're going to do has a lot of it. So we're just going to keep working at it. And yeah, and anytime you get to a question in the workbook, if you're like, how did you know this was that? There's two methods you could do. Number one, the skinny triangle trick works pretty darn well in a pinch. So never use a 45 degree, always use like a 20 or a 30 degree angle. And you could just see the answers usually. The other way is I'll teach you. And the third way is office hours. And then I don't know, after that, we could look around. Is that good for now, Jake?
Yeah, that's fine.
Yeah. So that said, why don't we get to the next one and look at it? Let's do 5.10. So I'll let you kind of think about it. You could draw whatever you think. I'm going to get it sketched up and then we'll work together, okay? So, and this is going to be another one of those ones where I sketch it and then draw it all over again. Okay. So we're told that you apply some force horizontally to this thing. Can you guys try and, can you think of any situation how this might occur in the real world? Is this even, could this ever happen?
Yes.
There it is. Do you see it? Let me scoot this way. So, right, the idea is if I apply a force horizontally and it's not sufficient, it could start falling down. That's what we're talking about right here. So I like to think about the problems like how they really happen in the real world, because then I could start to care. All right. All right. So in this case, let's say we go like this. The first thing I want you to think about is this. Vectors can be moved around anywhere we want. It's convenient to not draw it this way. Pushing on it like this would be the same thing as if I had, and let me do that in blue, I think. I could actually apply a force this way, and that's the same thing. All I'm doing is I'm putting the tail of the vector on the force. That makes it easier for me to draw, and that's supposed to be an arrowhead. Okay, so I got that force. Give me another force that acts on this thing.
Gravity.
Gravity. Now I'm drawing this really big just so I can see the angles well. Remember, we're going to redraw this in a minute. So that's mg. Got it. What's the other force? Somebody else.
Normal force.
Which way does that point?
Up left.
Like that. Good. Perpendicular to the surface. Outstanding. Now, is this thing accelerating? Before we go on, let's read. Let me just bring it up on the screen. Okay, blah, 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 blah. It's insufficient. Okay. Okay, it's accelerating. Got it. So it's accelerating down the plane. So it's accelerating down the plane. Now, you could do this problem any way you want. We could use a normal XY coordinate system. I don't want to do the problem that way, but I'm going to show you that way after we do it the way I suggest. So if you're thinking, why don't I just use X and Y? It's not a bad thought. I'll show you why I prefer this other method first. So what that means is I want to do the rotated coordinate system, where this is X and that is Y. I'm going to draw this a little better in here. You'll see why. All right. Okay, so we've got X and Y. Sorry, I doodled there. All right. So based off that, we're going to need to split up these forces. Okay. Extend that normal force vector backwards. Trying to just draw that so you can see it. Okay, let's do our angle game. What's this angle?
90.
90. And then Jake, you were the one asking about the angles, right? So I'm going to put you on the spot. What do you think this angle is up here?
90 minus theta.
And then what's kind of giving you that idea? What kind of...
Well, I mean, all the angles in a triangle have to add up to 180.
Yeah, exactly. So this is 90 minus theta. Sorry, I couldn't squeeze it all in there. That looks terrible. How about I write it like that? Sorry. It looks goofy, but whatever. Okay. So what's this angle?
Okay. Well, so that whole corner is 90. So
That's 90.
it
I
has
agree.
has to be theta then, right?
Exactly. Now, based on our skinny triangle trick, at least one of the angles is really small. Does that make sense with the skinny triangle trick as a confirmation? Theta here is what? Big or small?
Pretty big. So yeah. Okay. Yeah.
All right. Take a guess. What's this one?
90 minus theta.
Yeah. And do you agree that this is now a right angle?
Yeah. Okay. Yeah, can kind of see that now.
Take a guess what this one is.
Theta.
Now, what if I had gone this way? What would this angle be?
90 minus theta. Theta. And, yeah, 90 minus theta.
And so look at this pattern. Every other angle is either theta or 90 minus theta. So if you do a good job drawing your angles so that one of them is significantly smaller than 45, you could just look at these and tell. Okay, so is this a correct free body diagram? Somebody other than Jake?
No.
No. Why is it not a correct free body diagram?
You have the ramp, right?
Right, and the ramp is a second body. Outstanding. Nice. I don't know who that was, but great job. So I'm going to take this, and I just want to remember here, I got this here. All right, so I got okay, I think I got this. I'm going to redraw it. Normally, I wouldn't erase this, but because I'm on a whiteboard and I have this much space, I got to do it. So you guys should not erase this. You should draw a second picture. I'll catch up. That, I think, is what we figured out was theta, right? Did I get that right? Hope so.
Yes.
And then this looks like theta as well, right? I could just tell the fat angle in this problem is theta. There's my picture. Now it's a little bit easier for me to write. What's this side? Is this going to be, whoops, excuse me, black pen. Is this going to be mg cosine or mg sine in this case?
Would it be cosine?
It is opposite. So nope, good guess. We're used to thinking that x-axis, and that's the problem. So this should be mg cosine. You see, I just said it too. It's mg sine. And I just want to point out, remember, so has opposite in it. And so because this side is opposite theta, that's why it gets the sine. Did that make sense?
Yeah, I did.
Nice. So, and you can see how easy it is to screw this up. So this side in here is going to be mg cos. Sorry, I have to write that so small and sloppy. Let's do this one. How about this component? What's that going to be? F sine or F cosine?
There'll be F cosine, I believe.
Opposite. Nope.
Okay, that'll be F sine.
Yeah. And so notice this gets tricky. This one, the X component gets the sine. This one, the Y component gets the sine, even though it's this. Oh my gosh, doesn't that drive you crazy? And so the only way to get it, of course, is shitloads of practice. That's not what people like to hear, right? Because it's not that you can't get this. You guys get it when I talk about it, right? That just means all you need to do is practice a lot. It's not what people enjoy hearing. Like, oh, great. So now I got to do boring practice for a couple hours. But I'll tell you what, right? You want to shoot free throws, you go out and shoot 100 free throws, you get better at it. You want to do force problems, you go out and do 100 force problems. Oh my gosh, you get a lot better at it. It's just practice at this point for you guys, probably. All right. All right. So now I'm going to do the forces in the X. So remember, it's arrows equals mass times acceleration in the X. And then in the Y direction, it's going to be some crap equals mass times acceleration in the Y. Let me get that down a little bit. Okay, so somebody shout it out. Give me a force in the X.
Negative mg sine theta.
Let me check. Mg sine theta. What do you think, Jake?
Yeah, that's on the X that we defined, right?
But you said negative.
Oh, we flipped the signs. Okay, positive.
Yeah, did you notice I drew? And so now I'm not trying to be a dick here. I'm just really good at it. But I'm doing this as well because you're going to get a quiz question. I don't remember if it's chapter 5 or chapter 7 or both. Or I mean, chapter 5 or 6, where I literally draw a picture, and on some places I give you this coordinate, on some I give you this, and so I basically just flip the arrows around. And I really want you to get in the habit of not only looking at this, but also that. It's the combination that gives you the minus sign. It's coming on chapter 5 or 6 or both quizzes, and I don't remember which. But yeah, so Jake, does that make sense what I was?
Yeah.
Always
That
double
got me
check
for a
arrowhead relative to coordinate. So based on that, I think you agree it's positive mg sign, right?
Yep.
I'll explain why I would actually prefer you to use this after we do the next part. Okay. So that was good. Somebody else, give me another force in the X.
Negative F cosine theta.
Is there anything else that's parallel to X?
I think that's it.
That's it. I think that's it. Okay. So what's the acceleration in the X direction? 0, right?
No, it's positive
No.
A.
It's positive A. And so that's the real reason I chose this here, is so that I can write MA. Furthermore, let's skip ahead. What's the acceleration in the Y direction? If you're only accelerating in the X,
0.
and so this is why we rotate the coordinates. This is one of the reasons. It's a lot easier to do algebra when one of the equations equals 0, it turns out. And it saves you a step or two. It's not like you couldn't have done it other ways. Any coordinate system you choose should get the right answers. But this one sets one of the equations equals to 0, which can speed up the math. That's all we're doing this for. Got it? Also notice the reason I set this as positive is people remember F equals MA. People don't remember F equals plus or minus MA. And so, Jake, if I had aligned the coordinate system upwards, you would have been right on this one being negative. But a lot of times students forget that, oh, shit, A should have been negative. And so no matter what you do, you're stuck always double checking this. And so I have found historically, if students get in the habit of lining up the x-axis with the acceleration whenever possible, they make fewer mistakes. And if you do that every time, you get used to it because you're like, okay, this is always MA, this is always 0. At least you have 2 pieces of the equation right every time, as long as you line up the coordinates with that. Is that good on why to do that, Jake?
Yeah, it makes sense.
I think you'll find it reduces errors, and I don't know. Or does anybody else have questions about that? Not just Jake.
I have a question of how would it be worded if it was if the acceleration was going towards the Y? If it was like in a different question, of course.
Yeah, okay. So let's I was actually gonna, right after we finish this, do it again in a different way that I think might answer your question. So is it okay if I hold off on answering that and then try it a different way right after?
Yes.
Right. And then if that doesn't answer it, we'll come back to it again. Okay. Okay. Give me a force in the Y, somebody. Kev, you want to try it out?
Sure. It would be negative mg cosine theta.
Yes. Somebody else. Next. Or are we done?
Positive n.
Positive N. I agree. Somebody else. Is that it or are we done?
Negative F sine theta.
Correct. Awesome. And then we're done, right? We got everything. And so again, this is 2/3 of the battle. You can see there's a lot of ways to make mistakes. One of the questions in your test or your quiz is going to be something like where I draw an FBD. Actually, one of them is I draw a bunch of different arrows, like 12 or 13 different sets of arrows. And I say, which one of these sets of arrows is the FBD? And then I'll say, which one of these best represents the X component of the force based on this? Is it positive F sine theta? Is it negative F sine theta? Is it positive F cosine theta? Is it F? Is it? And so there's like 10 different choices for the arrows. And so basically you have to know how to draw this. You have to know how to split up these into components very, very well. Okay. So all the time, this is where you need to focus most of your work. At this point, we could solve for something. Let's read the question. Figure out F, figure out N. Got it. So at this point, well, F's pretty easy. Notice we get this similar thing where one of them ends up kind of easy and then you plug it into the other one. Trivial. Okay, before I go on, memo. Is there anything you want to tell the students about what you learned? How do you recommend they practice? Is there any advice you have from your experience in Physics 110 and 161? So I'm going to go to gallery view so I can see, or memo, if you could, are you there?
Yeah, I'm here.
Are you able to turn on your camera for a second?
Yeah.
Sweet. I appreciate it. So Memo, any thoughts you have or advice based on how you practiced or anything like that?
Advice. Let's see. I know you can miss some things on these like free body diagrams. I have missed drawing forces and stuff. So I would just go over the problem as much as you can and like just try to think about it and draw every force, everything that you can think about, and it makes sense to you. Like you shouldn't have just one force in the Y if like unless it's accelerating, but if it's not moving, then you should have some couple forces in some direction so they can cancel out if it's not moving. Just because you can get stuck like that, or you can just things. So just draw your pictures. Really draw your pictures. Get into the habit of drawing your pictures now. That way, if you're an engineering major, once you transition over, it's going to be helpful because you go way more into detail.
Yeah, in your engineering classes, you have to draw your pictures to scale all the time, right?
Yeah, it's not the math that takes forever. It's just the pictures. It's the pictures that will.
Pictures totally take forever in my job all the time. Everything is, yeah. But the thing is, if part of science is communicating with others,
yeah. Oh yeah.
Pictures help you communicate, so you've got to be good at it.
Pictures, yeah. You got to be really good at pictures. It just helps.
Yeah. How about when you were doing them, Memo? So these chapters 5 and 6. So I guess what I would recommend to students is try to draw the picture before you look at the solution, and maybe draw the picture and write the force equations before you look at the solutions. Yeah. But double check with the solutions before you go on.
Because you don't want to kind of like have your time being wasted. Not necessarily wasted, but just going down the wrong direction, and then
right.
These angles can be pretty tricky. Yes, I can't get the hang of it sometimes, but it's pretty good.
Yeah. Okay, so then it sounds like Memo agrees where it's good to, rather than have the solutions open, try to draw the picture, write the force equations, then immediately go check. and you'll get lots of practice. And I drew lots of pictures in the solutions too.
Yeah, if you can get your equations right, and then just keep on going.
Yeah.
Just check your equations, and then I'm pretty sure everyone else can do the work.
Yeah, exactly. Algebra you get good at by just doing. I mean, you have to do the algebra too. You can't get lazy and skip the algebra, but the algebra will get so fast. That's not the issue for you. It's the pictures.
Pictures, definitely.
All right.
And then just thinking about them. Just the x, just like the axis that sometimes drawn, they can be tricky. Sometimes, like, what's the best way to go? Or just thinking creatively. I guess it's kind of hard.
Yeah.
More practice, it helps you.
Exactly. The more you practice, the better you get at. You basically have better experience and you have better judgment, because there's a lot of problems where you have to kind of guess a little bit and be like, I'm not sure what the right approach is, but I've seen other problems that look like this and I tried this. Why don't I start with that? And that you only get by practice. All right. Thanks, Memo. So let's go back. Do you guys have any questions for Memo or myself? Or remember, you could always chat with Memo or any questions before we go on. Thanks, Memo. All right, I'm going to get back to Kevin's question. Actually, let's go look at the solution, see if there's anything I forgot before I address Kevin's question. So this one, does anybody see something that I did badly here in the picture?
No, I thought I had something, but no, I don't.
Well, let me ask you this. In the work that we did on the whiteboard, was theta the skinny angle or the fat angle?
It was the fat angle.
Yeah.
Oh, okay. I see now.
And so I need to redraw that a little bit better. And I'm going to do that, and I just haven't had time. Go figure. So, yep, there's a case where I did a bad job drawing a picture. Most of the rest of them in there should be to scale, but I need to fix that up so I'm not confusing students. So I did a bad job there. The equations are all correct, and they all look the same, but it's nice to have the angle be right in your picture. So I added a risk of confusion. That doesn't do anybody any good. When you're communicating with others, the less people have to think about, you know, how to manipulate your picture and make it match the real world. The less people have to do that, the more they can focus on what you care about. All right, so there's that. Another thing here is what is the point of all this nonsense? You might be saying, why are we just playing with a bunch of letters and moving them around? Well, the idea here is this: we get these equations, and here's an equation. What if I was designing some kind of winch or something, and I wanted to lower an object at a certain known acceleration? Well, this would tell me what force the winch would have to apply. And then I could say, well, I know I need at least this size cable, blah, blah, blah. So the idea is you can use these algebraic equations to help you design real life objects, right? So if you know, or maybe you'd say, well, I know my winch can support this much force. I know I want the object to go to this acceleration. That tells you a limit on the weight or the angle. And so this helps you design certain systems. Or down here, you could solve for this normal force. And at this point, you could say, well, if I want this to support this acceleration, I need to make sure my materials can withstand this much normal force. Or if you know your materials can withstand this much normal force, it tells you a weight limit for your ramp. So I know I'm not necessarily making the best out of this, but the idea is you solve these problems algebraically, because then you could say, well, what do I care about? What do I need to have happen in my real life object? And then that helps you adjust the parameters and set limits on how safe it is. So that's one way you could apply this stuff to the real world. It looks really cheesy right now, but so when I get that new, I'm going to spend all my money on an AI robot that can push erasers and cause them to lower them with constant acceleration. And boy, I need to know that horizontal force to apply for my AI robot. So that's why I was doing this problem. All right, whatever. All right, now to Kevin's question. Give me a second here. So we're doing the same problem in a different way, I think. And then I'm just going to get a little bit lazy here. Here's mg. We had a normal force that was pretty far over. And then we had a force applied this way. And now I'm not sure if this was Kevin's question or not. I hope it was. It was hard to communicate on the internet, you know. But I'm assuming, let's say we did use a normal XY. So Kevin had said, what if we use a different Y axis or something? And then I hope this question addresses it. If not, we'll revisit your question right after, Kev. In this case, I'm going to use a normal XY axis, X and Y. All right, help me. Tell me what the forces are. And you could actually, why don't you do this? Write down the forces in the X without talking to me, and write down the forces in the Y without talking to me. I'll do it as well, and then we'll compare. And if it helps, remember, that was theta, right? So what's this? Theta or 90 minus? And then what's this? And then what's this? So think that through. What's dot, double dot, and triple dot? I'll give you a second. I'll give you 1 minute. Cool, J-Dog. Okay, so you've had a minute to look at it. So hopefully you thought, if this is theta, that means this is theta by alternate whatevers. That means this angle is 90 minus. That means that angle is theta. So that's what jumps out to me. So I'm going to split the force up this way. Adjacent, adjacent, opposite. You could have done 90 minus theta. That's fine. Now that I've got my angles figured out, I'm going to get rid of that. And in the X direction, I see F minus n sine theta. Down here, I get So I'm going to pause and see if you guys buy into that. What do you think? Does that make sense? Or any questions on any of the sine, cosine components, thetas, plus minus signs, anything? Doesn't that seem a lot easier?
Yeah, looks good to me.
Right
Yeah.
now it does.
So what's the trick? What's the hard part?
Finding the acceleration.
Exactly. This acceleration, which way is the acceleration going? The acceleration was going which way?
Down to the left.
This way. Now, using our angle trick, does this upper angle or does this lower angle look like theta? Which one of these? Is it upper or lower?
Upper.
Exactly. So that skinny angle trick is pretty handy, right? So now, if that's A, what's AX?
Negative a cosine theta.
Let me think. Yes. Because this is A cosine theta to the left. Ugh. And so there we see that all the time we save doing this, now we have to add it in. We spend a lot of time on this. So, and I'll go into this in just a second. So this would be, what's AY going to be?
Negative a sine theta.
So notice we have to remember not only to split this up, but also whether it's plus or minus, and it starts to add into the complexity of the problem. I want to point out, how many vectors did we have to split up in this case? 1, 2. In the last version, when it was rotated, we had to split up these two. It's the same. 6 of one, half a dozen of the other. You're splitting up two vectors either way. Now, what I have found is students tend to screw this up more often than not, because everybody's like, oh, F equals MA, F equals MA, and they forget the minus signs right here sometimes. That's what I have noticed in student work. That's why I tend to align my coordinate system with the acceleration whenever possible. And Kevin, did this address your question or not?
Yes, it did.
Yeah. So you could use any coordinate system you want. Now, remember, the equations are going to look different, but the answers to those fundamental questions should be the same, meaning, I'll point this out. Oops, give me just a second. This answer and this answer should not depend on the coordinate system. What changes is how difficult it is to do the math. Again, you can use any coordinate system you want, and it's going to change the way the equations look. These equations look totally different, but in the end, when you rearrange and solve for something, we'll get the same answer. And so in this particular case, it looks like it's actually easier to solve for n in this set of equations, and then you plug that in and get f. So we see that sometimes it looks totally different, but you get the same answers. What do you think? So far, so good? There is a really good application for this, and I want to show you something. Oh no, did I lose it? Give me just a second here. Oh, there it is. So I just want this problem's a little bit different. So this is one that has friction, and we'll do that in chapter 6. But I just wanted to point out the way we've been doing these problems is we would split it up and it would look a little bit like this. And notice you could actually learn about the frictional force. Now we'll do that in the next chapter. But it looks very similar to what we just did. There's a bunch of words over here. Who cares about that crap? Now, this is the way it's going to become natural. You will find that you get used to this very soon. Now, the interesting thing is, notice on the same page, I did it the other way too. And the idea is this picture down low is great for plugging into a computer for coding. Because when you code something in Python, you usually use a standard XY coordinate system. So it turns out knowing both ways ends up helping you in the long run. And shocking, both ways are shown on the quiz. And some people are going to have the rotated and some people are going to have the unrotated. And so you got to know both because you never know which coordinate system you're going to get. Sometimes I put X this way. Sometimes I put X that way. Sometimes I put X this way, that way. Y could be this way, that way. That doesn't matter. All that does is it changes which forces get split up and the plus minus signs of everything in the whole equation. Is that good? I hope so. That's actually it for today. So we could call that good. Yeah. I guess I'll go ahead and maybe I'll send this out to the class as an announcement, but I forgot to say this to the other class. Some problems that would be good to do are all the problems up to probably 5.13 and 7/8. Yeah. And then next time we'll pick up on Newton's third law. So I'm going to send this announcement to the class immediately after I stop the live stream. I'll just tell people to finish all the problems up to page 87, including 5.13 and 7/8. Yeah. Sorry for the fractional numbering. I basically just wanted to squeeze those problems in, and I didn't want to have to renumber everything. I didn't start the book very intelligently with an auto renumbering, and I'm like, oh man, I didn't have to renumber everything in the solutions, and there's cross references. So sorry about that. It doesn't matter. They're just problems. What do you think, Memo? Books changed a lot since when you had the class, huh?
Oh yeah, books changed a lot.
Yeah.
Material.
I've rearranged it quite a bit. So, yeah. Any closing thoughts you have for the class about forces or practice or anything?
Just keep on practicing. Come to help. If you guys need help, email me. More than happy to help you.
Right
We
on.
can
Go
go
ahead
over
and
these
throw it in there
problems.
again. Throw in that email again just to remind them. That way they don't have to look.